Here's where we met off last time we met with comparing a carboxylic acid to an alcohol. So here's a big table of various carboxylic acids. And I looked through here this morning and saw that oxalic acid is about the strongest natural type of acid. An unnatural type of acid would be like the trichloroacetic acid. You don't find that in nature. You find oxalic acid in nature in rhubarb leaves. Don't want to eat them. Calcium oxalate will precipitate in your body and tear up your kidneys. So, as I said last time, some of this is a review from like chapter 2 in the fall. Here's that trichloroacetic acid. Of course, this is man-made, and you see this inductive effect. So we put more electronegative groups on there. It's going to make the acid stronger. And here we've seen the same slide in the acid chapter. The closer it is here, the more effect that inductive effect has on the acidity. So at the beginning of this chapter, I'm like, oh, what a boring chapter. But I just redid all the slides and a lot of neat things that should be kind of a review. So here are some aromatic carboxylic acids. You'll recognize this as benzoic acid. And as we put different groups on here, notice this is an electron withdrawing group. So when this is deprotonated, it helps stabilize the negative charge on the conjugate base. And it says the effects are strongest for substituents in the ortho and para position. Looks like para. See, we can compare all three of these positions with the nitro group. How do we name carboxylic acid salts? So here's pentanoic acid. Here's lithium hydroxide. So we named this lithium cation first. Then we named the anion by replacing ic acid with 8. Notice it's the reverse of what you learn in general chemistry. If you have the sulfate, becomes all right, let's do nitrogen. If you have nitrate, it becomes nitric acid. If you have sulfate, sulfuric acid. Same type of thing here. Take off the ic, and so it becomes a O8. So here, butanoic acid. Here, the ammonia. We formed the ammonium cation, so this is ammonium butanate. So properties of acid salts, usually solids. They're not very volatile, so they don't have much odor. Carboxylic salts of sodium, potassium, lithium, and ammonium. These are the things that render anything soluble. Those are soluble. All right, soap is the soluble sodium salt of a long chain fatty acid. So we might learn the difference between soap and detergent. Salts can be formed by the reaction of an acid with baking soda here, of course, releasing CO2. All right, so here's our triglyceride. This is why you don't want to eat a bunch of bacon and die of a coronary heart attack. All this triglyceride. But if you didn't have a big box store to go to when you came across the prairie, you would keep all your frying pan drippings. Every time you cooked anything, you'd save the fat. And then you would save ashes from your campfire and make a thing called lye, which is a mixture of sodium hydroxide and potassium hydroxide. And then you mix the lye with the fat, heat it up. Hydrolysis occurs. Hydrolysis means to split with water. You split that off. And now we have fatty acid salts. So if we had sodium here, we'd have the sodium salt here. If we had potassium, lye is a mixture of both potassium and sodium hydroxide, you'd have the sodium salts. All right, for fun, what's the difference between soap and detergent? All right, modern day detergents have a sulfone group or phosphorus, but they work the same way. In fact, let me fix this up. I think that's more proper. And how does soap work? This part is soluble. This greasy tail, remember aliphatic means fat-like, so you got fat ring around the collar. And the piece of dirt, the detergent forms a little micelles around it. There's the polar head, and it makes the dirt soluble in the wash and washes it away, just in case you forgot that micelles. Any questions? No questions? Pronounce this word. Saw pontification. turning fat into soap. Probably going to see something like it here at the end when we talk about esters. Extraction of carboxylic acids. So here's our carboxylic acid. It's in the ether phase. And when we add some dilute sodium hydroxide, it protonates like our benzoic acid. So the sodium salt, very water soluble. It's going to separate that from other organics. And then we can pour off the ether phase. When we acidify the aqueous phase, we can put it back into the ether. So the carboxylic acid is soluble in ether, not water. Make the sodium salt become soluble in water, but not ether. Protonate the carboxylic acid back to its original form, will be soluble ether, but not in the water. So here's how we shake and drain and pull out impurities there, pull off impurities in the ether phase there, and put it back in the ether phase and pull out impurities there. Now, if we had something like 2-naphthol in here, we'd want to pull the benzoic out with sodium bicarbonate. We'll pull the benzoic out, but the 2-naphthol would be left in there. Then the sodium hydroxide would pull out the 2-naphthol to make this relatable to what you did late last fall. It's called 2-base extraction. Important carboxylic acids. Acetic acid's got to be number 1. It's naturally occurring in the form of vinegar and used for Italian dressing and mustard and a bunch of other condiments, but industrially as a solvent, catalyst, and of course a reagent for various organic synthesis. Fatty acids from fats and oils. You just saw the formation of soap. Lauric acid. Benzoic acid is found in drugs and preservatives. So sodium benzoate. It's in practically everything. Processed food as a preservative. And if you're trying to not eat a lot of sodium, avoid those processed foods. Adipic acid. You made that in lab with potassium permanganate and your cyclohexene, used to make a polyester. Nylon is a type of polyester. Phthalic acid is used to make other polyesters. Plastic water bottles and soda bottles made from phthalic acid. The number 2 on the recycling thing. So I said this chapter was exciting because of all the review things you should know, but it's the end of the semester. You need a good review. So carbonyl carbon, I always think about 1720, give or take. There's 2 features in the RIR spectrum of carboxylic acid. Big, intense peak, normally the most intense, goes all the way down to the bottom. And the big, wide OH peak. You can't miss a carboxylic acid, and conjugation lowers the frequency of this band. So you see this thing's conjugated. I think an ester moved it to like 1730. So I skipped the picture of the IR spectrum. Carboxylic acid protons are the most de-shielded we have encountered, absorbing between 10 and 13 on the chemical shift. Let me just ask you a question. What does this peak look like? Some little trivia. Let me give you a hint. Looks an awful lot like maybe a peak on a hydrogen oxygen or a hydrogen nitrogen. What does that mean? That means it's acidic proton. Does that mean it's a nice sharp peak or a wider peak? It's coming off and it widens up. That's one reason why we don't normally see the splitting. And then our normal, these ones right here are kind of close to that de-shielding system. 2 and 2.5 chemical shift value. So here's this broad peak. It's over here at 11.8 or something. That's what this means. And then we should see a triplet. We should see 6 peaks, 2, 3, 4, 5, 6. And this thing, another triplet, triplet, triplet. How many different carbons? 1, 2, 3, 4. 1, 2, 3. Ignore that. That's the solvent. There's our 4th. So here's the carbon-13 spectrum, proton NMR spectrum. Now the exciting part, at least it's exciting for me, the mass spec of carboxylic acids. What's going to be the telltale signs in the spectrum? So you've seen this before when we did an aldehyde. We had an unknown, we knew the molecular formula, and we deduced that it was like butanol. So aldehydes and possibly ketones and carboxylic acids can all do this thing called a McLafferty rearrangement. So you need at least 1, 2, 3, 4 carbons. And you can see almost a perfect 6-sided ring there, which allows these electrons to grab that hydrogen and that to jump over there and kicks off that. But here's what I think is the interesting thing. Even another common fragment is cleavage of the BG bond form. I think those need to be Greek letters and it would make more sense to form an alky radical and a resonance stabilized cation. So here's our mass spectrum. So I always preach about most hydrocarbons, carbohydrates, they all have an even mass and odd fragments. So whenever you see an even fragment, you go, whoa, what's going on? So the first one we learned about was -18 when we lose water from an alcohol. Well, this is a lot greater than 18, probably not an alcohol. So what's going on? What's going on? I didn't bring my calculator to add up integers real quick. 3 times 12 plus 6, 24, 36, 12. What is that? What I'm at? 48. But here's our 60. There's our base peak. What's this 73? Alpha, beta, gamma, epsilon, beta through whatever G is. What's G on the Greek alphabet? Yeah. All right, gamma. Boy, don't I feel stupid. I'll have to edit that out. It's gonna put it up for the world to see. All right, how can we make a carboxylic acid? Think about the alcohol chapter. Primary alcohols. Yeah, potassium permanganate, the sodium dichromate, oxidation of primary alcohols and alcohols with chromic acid or the permanganate. We're going to get them all. So I said, good review from the alkene, the alkyne, the ketone aldehyde chapters. We all kind of get all those coming back to haunt us in the carboxylic acid. Cleavage of an alkene with hot potassium permanganate produces a carboxylic acid if there is a vinyl hydrogen, vanillic, that's how I like to say their flavor, vanillic. Ozonolysis of an alkyne. We think of any more? Alkybenzene, the side chain oxidation. That's the last thing we learned in chapter 17. All the different ways to make a carboxylic acid. Here's the more green version, use bleach. Here's the chromic acid, primary alcohol, hard to stop. You do want to stop it. What's the acronym for the reagent you use? PCC. So here in general, you're kind of specific by this chromic acid, mixing sodium dichromate and sulfuric acid. And you can use potassium permanganate. I think this is a little more greener. So we cleave this, put an oxygen on each side. This is where we get the carboxylic acid. Here's where we get the ketone. So first we form the glycol, and then we get the acid and ketone. And if this was another alkyl group, we'd get 2 ketones, depending on the substitution of the original double bond, ketones or acids. Here's our alkene, chapter 9, and 2 carboxylic acids. Ozonolysis or vigorous potassium permanganate. And this last thing, side chain oxidation. So here's an alkyl group. Could just be a methyl, could be an ethyl. Here we got isopropyl. These oxidizing agents don't discriminate. They just take it, chew it all up into carbonyl, carbon, and an acid there. Now onto something new. Carboxylation of a Grignard reagent. So this is CO2. So you can do this with any organometallic for the most part. You take your organometallic, Grignard or lithium, or I wonder if some of those Gilman reagents might work, and you pour it on some dry ice that you crushed up. And there might be some other methods. And so this carbon is kind of negative, and this is definitely, that was a Freudian slip. This thing's rather positive, and you always want to think of the Grignard as being strongest base known to mankind. Slams in there, does its thing. So here's bromocyclohexene, form the Grignard, carboanion there, slams into there by the time you protonate it. Cyclohexane carboxylic acid. Reviews our nomenclature from Wednesday. Sometimes called CO2 insertion and it increases the carbons in the molecule by 1. Something new here, maybe new. Trying to remember the aldehyde chapter. So alkyl halide, cyanide is a good nucleophile. This is going to be an SN2 reaction, and it's called hydrolysis, splitting with water. What are you splitting? You're splitting off this nitrogen. It can be basic or acidic. You get ammonium cation and the carboxylic acid. So there's a general case. So we can get benzyl bromide, SN2 it with sodium cyanide, get phenyl acetylnitrile, hydrolyze the double bond, and now we have phenyl acetic acid, basic or acidic hydrolysis of a nitrile group. Kind of similar in that if we have some target, our starting material probably needs to have one less carbon than what we want. So we're going to put that's where the carbonyl carbon goes. You can read that later. It's not too important. The group bonded to the acyl carbon determines the class of compound. Some of these we've seen before, maybe some we haven't. When we have an OH bonded to a carbonyl carbon, we have a carboxylic acid. If we have a chlorine, we call it an acid chloride or acid bromide. When we have an alkoxy group, we have what we call an ester. When we have nitrogen, we have an amide. These interconvert via nucleophilic acyl substitution. Who knows what this is right at the moment? We don't care. Nucleophile slams in there. Chemistry magic occurs. There's the nucleophile. There's like a leaving group. And so here are our acid derivatives. Carboxylic acid, acyl halide. That wasn't mentioned on the slide. Here's anhydride. So in the aspirin lab, you made acyl salicylic acid using acetic anhydride. You made an ester, and then here's a amide. Carboxylic acids react by nucleophilic substitution where one nucleophile replaces another on the acyl carbon. Now we see it in action, and you just saw this with the soap. Basic hydrolysis of an ester, where we got glycerin over on this side, and we had the big fatty chain. Hydroxide slams in there, those electrons jump up. So here we have this tetrahedral intermediate. These electrons jump down, and this leaves. And I'm always a little bit hesitant here because I'm all about acid-base chemistry, and I would say alkoxide is stronger than hydroxide. Doesn't matter in the end. Got to see the big picture. Right here, proton transfer. My alkoxide I just made pulls this off, and now I have a carboxylate. And a carboxylate is definitely not as basic as this thing here, especially if we go back to the beginning and look at the conjugate base of a carboxylic acid versus an alcohol. This is the conjugate base of an alcohol. This is the conjugate base of a carboxylic acid. And so nature did drive us to form a weaker base, if we look at the big picture. And who knows, in nature, maybe the hydroxide could fall off and then it could hit again. And, we could probably have an energy diagram with two peaks that aren't very much different in energy, maybe kicking this one off higher in energy, but it just cycles around, and this drives it to the end, forming the weaker base. So here is the banana oil lab. You took acetic acid, isoamyl alcohol, and made the banana oil, the ester there. Here's a ethyl acetate. Here's a dimethyl phthalate. So we see the equilibrium arrows. Here we have a value, it's greater than 1. And we probably jack up one reactant. Now on some of your labs, the question was, how can we drive it? And unfortunately, a few of you said, use a lot of reactants. No, you can only use one. If you jack them both up at the same time, it doesn't work. You need a large portion of one and just a normal portion of the other. These are always equal. We can't force things to the other side with Le Chatelier's principle. Large excess of alcohol, perhaps. And many times the excess reagent is used as a solvent or removing product as its form, product or water. And of course, you know the mechanism already because you wrote it in your lab book, but we can review all carbonyl carbon chemistry, acid catalyzed. First thing you generally do is protonate oxygen. That makes this more susceptible to nucleophilic attack. All right, now we have a tetrahedral intermediate. From there, A couple things we can imagine. We can deprotonate this, and now we have a ester hydrate. Little review from the chapter 18. So there we get to the hydrate. And now notice it doesn't matter which one we protonate, they're equivalent. You protonate the OH, turns it into water, a good leaving group that can leave, and that will be protonated, and then that pulls off, and we've regenerated our acid catalyst. And there we have our ester. So here's something completely new, something we'll never do in lab. If you go to graduate school and do a lot of synthesis, you might use this. Industry uses it, but it's very tricky to use because it's, I think it's deadly toxic and explosive. And it's only generated as you need it, diazomethane. And notice no equilibrium arrows. It's fairly general. This thing would be a hard thing to make. I think this thing would be kind of reactive. Converted to their methyl esters very simply by adding an ether solution of diazomethane. Of course, the diazomethane is the tricky thing to work with. The reaction usually produces quantitative yields, 99.9% yield. Very toxic, very explosive, yellow gas. And here we get to see what it might look like. And so we can draw two Lewis structures. Here's this negative thing. Looks like a fairly strong base. Pulls that off. And now we have this positively charged species, methyl diazonium ion. And then this thing undergoes nucleophilic attack right on this carbon. And look at this wonderful leaving group, nitrogen gas. There's nothing more inert and almost non-toxic than nitrogen gas. It's non-toxic unless it displaces all the oxygen you're trying to breathe, right? Synthesis of amides. I want to talk about peptides and proteins, carboxylic acid, an amide, acid base. It's kind of like an ammonium salt. And then you heat this thing up, drives off water, and you formed your amide. You got to heat this to well above 100. This is definitely not the way living organisms do it. All right, this is probably a good place to stop.